Well, it's good to see you again. We're now going to begin a very important chapter on heat and the second law of thermodynamics. Now, we will have just covered energy in all its various forms and the first law of thermodynamics. And in the first law, we talked about how there is so much energy in the universe and that this energy can be interconverted between different forms. In this chapter, we'll see that we have some other things to worry about. We will see that even though energy can be interconverted between different forms, it becomes degraded with time due to the second law and what is called entropy. Entropy happens. The second law of thermodynamics tells us that the disorder of an isolated system, and when we say isolated system, we can also substitute universe. The disorder of the universe increases with time. That is, disorder increases spontaneously. Things get scrambled up. Things get messy with time. That is a natural tendency. That's what we'll learn in this lesson. And in this lesson, we'll talk a lot about heat. And we'll see that heat is a form of energy. It is in some sense a degraded form of energy. It is a form that flows from higher temperature to lower temperature. And this flow of heat from higher temperature to lower temperature can be used to do work. But in many cases, we'll see how heat is associated with this increase in disorder. And through our discussion of heat, we will see the connection with this second law of thermodynamics. Now, this slide just reminds you that you should have watched the lessons on temperature. And if you have not yet, you probably want to pause and go back and find the lessons. There are 2 lessons on temperature because you'll need to understand temperature before we can cover the rest of this chapter on heat. Heat flows from hot to cold. Now, this is our common everyday experience. If we take some ice from the freezer, we put it in a cup of lukewarm water or hot water, what happens? Thermal energy flows from the hot water into the ice cube, thus melting it. Common everyday experience. If we take a cone of ice cream and we put it on a counter, it will melt. Thermal energy is flowing from the atmosphere or from the counter into the ice cream, and the ice cream melts. I mean, this just happens. This is our everyday experience. We can't imagine it to be any different. We can't imagine a glass of water, for example, spontaneously forming an ice cube with the rest of the water getting even hotter. It just doesn't make any sense to us. So our common observation is that heat flows from hot to cold. Now, here's a little video showing this effect. And you'll see that if you take some ice cubes, you put them on a counter, a warm counter, or at least not a cold counter, that as a function of time, the poor little ice cubes melt away into a sad little puddle of water. We see this all the time. We see this all the time, and this is an example of what we are talking about, how heat flows from the counter or from the air in the atmosphere to the ice cubes, melting the ice cubes. It's just the world around us. The question is, why? Why does that heat flow, and what are the consequences? First, let's talk about what is heat. Heat, which we will also refer to as thermal energy. Heat or thermal energy is a type of energy that is contained within a substance. And sometimes we'll talk about it as being a type of energy that is transferred between substances. Now, heat is not the same thing as temperature, as we discussed in the lessons on temperature. Temperature is an intensive measure of the quality of the substance. Think of temperature as degrees. Whereas heat is an extensive parameter. It is a quantity, an amount possessed or contained within a substance. The heat or thermal energy of a substance will depend upon its temperature, the amount of the substance, and the nature of the substance. Now, the first is fairly obvious if you look at my square to the right. If you have two blocks of iron, for example, one at 50 degrees and one at 20 degrees, obviously the block at higher temperature contains more heat, more thermal energy. But let's now consider two blocks of iron, both at 50 degrees Celsius, but one is twice as large as the other. One is 100 kilograms, the other is 50 kilograms. The larger block contains more thermal energy, more heat than does a smaller block. So, in the old days, they would heat up a brick or a stone and put it in their bed for warmth. So you would want the larger brick or the larger stone because it contains more heat. Now also, to warm up the two blocks of iron of different size from 20 to 50 degrees, it would take a greater input of energy from another source to warm up the larger block than the smaller block. If you look at the drawing at the bottom, where you have a constant input of thermal energy to these two blocks, it takes longer to heat up the larger block, or it takes a larger input of energy from another source. So to summarize, the heat or the thermal content of an object depends upon its temperature, the amount of that substance, and it also depends on the nature of the substance, which we'll talk about in the next slide. If you have a 1 kilogram block of aluminum, it can hold more heat than a 1 kilogram block of iron. You may not know that, of course, but that is in fact the case. It has to do with something called the specific heat of the two elements. Also, a 1 kilogram container of water will hold more heat than a 1 kilogram block of gold. And this is illustrated in the graphic that shows that if you have a 1 kilogram block of gold and a 1 kilogram body of water in some container, and you tried to heat them up with a constant source of heat, it would take 30 times longer to heat up the water than to heat up the gold. That is, water can hold more heat, but you also have to input more thermal energy to elevate its temperature. So different substances can hold more thermal energy, and it also takes longer to introduce that thermal energy and for it to be removed from that substance. Relative to other substances, just as an aside, water takes a lot longer to heat up and cool down. It stores heat well. Now you might have noticed this if you have a pan of water on a stove and you boil the water. Of course, at some point in time, both the metal of the pan and the water are at the same temperature, 100 degrees Celsius. But if you take the water from the pan and pour the water into another container and set the pan aside, the pan will actually cool down more rapidly than will the water. Water will hold heat for a longer time. Again, it has to do with something called the specific heat of water. Heat can flow between substances or between objects in three different ways. One is by conduction, and I show in this graphic a fire and the three different ways that heat can flow. If we look first at the conduction, if you take a piece of metal poker, and you place it into the fire, the thermal energy will be conducted, and if you're not wearing a glove, it'll become hot and you will feel it. Thermal conduction occurs through the object, and we'll talk a little bit more about it in the next slide or two. Convection is another way that heat flows. Convection involves the actual movement of molecules of, in this case, air, or it could be water, as a group of molecules sort of percolate up. That is the process of convection. Radiation is a little different. It involves electromagnetic radiation, infrared in most cases. So these are three different ways that heat can flow between hotter objects and cooler objects. And we'll talk in the next slide about conduction in particular, but let me, as an aside, talk about the importance of heat flow in biology. We are warm-blooded creatures. Many animals are warm-blooded. And that means that for us to function well, we need to maintain our body temperature at a constant temperature. And of course, that's 98.6 on the Fahrenheit scale or 37 degrees on the Celsius scale. Animals can maintain their body temperature by the following ways. They have, first of all, have insulation. Animals have fur or feathers or fat, or we humans have our wardrobes, which help us minimize the loss of heat. Animals can also increase their internal production of heat through shivering or something called brown fat. So when we're cold, we shiver or we produce more heat internally. Also, some animals can increase the rate at which they lose heat through perspiration or the dilation of veins. Actually, when we blush, that's an example of the dilation of the veins near our surface of our skin and how we can lose body heat in that way. So, just a digression of how heat flow is also important in biology. But let's go back to our discussion of conduction as a mechanism for heat flow. Now, you know, if you have two blocks of iron, let's say, one at 50 degrees and one at 20 degrees, one hot, one cool. Two blocks of iron, as I've illustrated on the left, and if you bring them together so that they touch, you know what's going to happen. Thermal energy is going to flow from the hotter object to the cooler object until, after a period of time, the two objects will be at an intermediate temperature. That is, there will be thermal equilibration. Now, how does this happen? Actually, this flow of thermal energy leading to thermal equilibration occurs through the transfer of kinetic energy through the atoms or molecules that comprise the solid object. In a solid, molecules don't really translate, don't really move around, but they can vibrate. And at the interface, the molecules from the hotter object will be vibrating faster than the ones from the cooler object, but there will be a transfer of this kinetic energy, of this bounciness, from the hotter to the cooler. And over a period of time, that thermal energy will then become equilibrated throughout the two metal objects that are touching each other. So that is actually the mechanism of conduction. And to show you a little more about how this works, the bottom right shows another graphic. This will apply to liquids or gases because the molecules in this simulation are actually free to move around, whereas in solids they're fixed in place and can only vibrate. But in liquids and gases, they can diffuse around. So, initially in this simulation, I will show two containers of gas or liquids separated, and you'll see that the ones on the left, the atoms or the molecules on the left, have more kinetic energy. They're moving around, zipping around more rapidly as compared to the one on the right. And then in the simulation, I'll bring them closer together, and you'll see what I mean by the transfer of kinetic energy from the left to the right. Let me get this started. So initially, the one on the left has more kinetic energy. Those guys on the left are moshing, and their molecules are zipping around much more rapidly. Then if I bring them together, you'll see initially the one on the left is moving, they're moving more rapidly, but now over a period of time, the two begin to move, or the atoms and molecules move at about the same speed. They have equilibrated. Now, this is our common experience, and what I want to show you is that the opposite does not happen. And you'll see in the next simulation that'll begin in just a second that if we have two sides separated by an interface that are at the same temperature, what does not happen is that the left side will gain more kinetic energy at the expense of the right side. And you can see in this example, the left side is now hopping around and the right side is slowing down. This does not happen. This is not our experience. And so in the next lesson, we'll talk about why this does not happen. Okay, so we will pause for a quiz, and when we come back, we'll talk more about what is called the second law of thermodynamics and why it is that hot and cold cannot spontaneously separate from one another, but actually the opposite occurs, that thermal energy flows from a hotter to a cooler object.